Now we summarize all of this information by writing the following. X has, tilde mean has, a binomial distribution with n trials and the probability of success p. Now, I want to emphasize the word success and failure are used only to distinguish between two possibilities. I'm going to do a problem in a moment here, or I'm going to examine a problem. In fact, it's going to be problem number, well, let's see. Number 23 on page 475. So we're going to look at to show you the limitations of the word success, we're going to have success and failure in this problem. And basically the problem is whether or not a child in England has rickets. Rickets is a disease of the thing in the bones. There's not enough strength in the bone because of deficiency of vitamin D. I'm going to call that success. I want to make it clear that when I call something success, there's no normative judgment, no moral judgment. In fact, we would want people not to have rickets. But I'm going to use success to note that an individual has rickets. All right, it's kind of a perverse use of the language. All right, now. Last week I talked about computing, or maybe even the week before, about computing binomial probabilities, and we had to talk about factorial, and we had to talk about this symbol here, which is expressed n choose x. And I finally came up with this little formula here. If x represents the number of successes in n trials, then x can take on any of the values 0 through n. And we can write the following: the probability that capital X, which represents the Venn diagram, takes on little x, where little x is one of these values, is computed by determining the number of common, or n choose x, that will be a number. P is the probability of success in a given trial raised to little x. And then I multiply that times 1 minus p, which is also represented by q. And the exponent there is n minus little x. That's how we do the computations. Now what I've done before is I've used Excel to compute these values. And in general I will do that. You should know how to use this formula in the sense I might give you a specific example on the final where I ask you to compute this. Yes?
I'm stuck at a pretty basic point. I still don't understand what n choose x even means in real time.
I'm sorry. What we have here is I have n trials. N is some number that will be determined in a contest. Generally, it should be more than 1. All right? Could be something like 100 or 1,000. Okay? Now, if I look at a string of successes and failures, and I'm looking at 1,000 of those, what is the possible number of successes? Could have few as 0. That's unlikely, but it's possible. You could have 1 success, you could have 2 successes, all the way up to 1,000. If I flip a coin, Remember, the best example of a binomial experiment is flipping a coin. Say 25 times. What I'm saying here is the following. N is equal to 25. I'm going to look at the results of 25 tosses of a coin. I'm going to call success, in this example, observing a tail. And I'm going to let x equal to the number of successes, that is tails. And the number of tails, if I do this 25 times, could be as small as 0. That's not very likely. But it could have 1, 2, 3, and so forth. The maximum number of successes I could have, or the maximum number of tails, is 25. Now what I would write here, first of all, the probability of success, that is the probability of observing a tail, is 1/2. Okay, that's typically the value we use when we're talking about flipping a coin. Now if I write the following, x has a binomial distribution with 25 trials and a probability of success 1/2. We can think of this as kind of a representation of the following. I have a table where I can, in fact, determine the probabilities for all the numbers 0 through 25. Okay? Now this formula here, if I wanted to know some specific value, suppose I wanted to know the probability that x is equal to 13. In this, using this formula, n for that would be 25, so I can have anywhere from 0 to 25 successes. If I choose a specific value of 13, then this would be 25, choose 13. P would be 1/2. I'd be taking 1/2 to the 13th power. And then I would take 1 minus 1/2, which is also 1/2, to the 25 minus 13 power, which would be the 12th power. So let me put that down here. Suppose I want to know what the probability of observing 13 successes. So the probability that my random variable is 13 would be 25, choose 13, 1/2 to the 13th power, 1 minus 1/2 to the 25 minus 13th power. This could be written as 25, choose 13, 1/2 to the 13th power, 1/2 to the 12th power. And if you remember your algebra, this is actually 1/2 to the 25th power because the base is the same and I simply need to add the exponents. What is this? So that's going to be 25 factorial. I take the n and I factorialize it. In the denominator, I take the 13 and I factorialize it. That's an invented word. I don't think there is a word factorial. And then I take 25, I subtract 13, and I take the factorial of that. Now we can go through the computation here, but in general, if we were to fill out a table, we probably want to use the Excel or some software to figure that out. Okay. So, now, this is the general description. If I'm going to be concrete, if you will, I have to tell you what n is, and I need to tell you what p is. Now, once I tell you what little p is, the probability of success, the probability of failure is automatically 1 minus that. Okay, now, so this is the general description, this is a specific example, and now what I'm going to do is I'm going to illustrate how we make use of these ideas. Okay, now before I do that, let me just go through this notation here. In this case over here, which is the general description, suppose I have a random variable which has a binomial distribution with n trials and the probability of success in a given trial p. What it means is I have a binomial experiment, I have n trials, and x represents the number of successes. Now, all random variables in this class have an expected value, all right, or a mean value. This over here is expressed the expected value, E, expected value of x. That quantity is also represented by the Greek letter mu with a subscript of x. We use a subscript of x, if you will, as a way of kind of identifying which random variable we're talking about. The expected value of x, or the mean value of x, when I have a random variable that fits this description, it turns out it's nothing more than n times p. So over here, in this case, what is the expected value of x? Well, it's 25 times 1/2, and that's equal to then 12.5. If I take each one of these numbers and multiply them times the corresponding probability and add them all together, it's going to be 12.5. It's not obvious that this is correct. It's a theorem in math. We can actually prove that. Now, random variables have variances. The variance of x, which is represented in this fashion or in this fashion. In this expression here, I have the Greek letter sigma. I have a subscript of capital X, and I have an exponent of 2. For a binomial random variable, the variance is n times p times 1 minus p, which is also q. So the variance in this case is 25 times 1/2 times 1 minus 1/2. Both of these are going to be a half. 1/2 times 1/2 is 1/4, so this will be 25 over 4. Now the standard deviation of a random variable is nothing more than the square root of the variance. And the square root of 25 over 4 is 5 over 2. It just turns out that these are nice values, if you will. Okay. Choose different values of n and choose different values of p. If you've got your own formula sheet, you can use that, just in case you didn't have it. Okay. All right, now, again, these facts over here are theorems. I'm simply stating them that they're true. All right, if you wanted to suffer for several hours, I might be able to convince you that these are correct, but we'll just take them as being true. Okay, now, the binomial distribution can be approximated by a normal model in some circumstances. These are the circumstances. If n times p, that is the number of trials, times the probability of success in a given trial, all the parameters I'm using over here, is greater than or equal to 10, and n times q, q is 1 minus p, if that product is greater than or equal to 10, then the binomial distribution can be modeled by a normal distribution, and I'll illustrate that visually in just a moment. Which normal model? Well, the normal model where mu is NP, that's the value I had computed for the mean, and the standard deviation where n is the square root of n times p times q. Now over here, in this case, n times p is 25 times 1/2, and that's 12.5. n times q is 25 times 1/2, and that's also 12.5. So we can approximate x by a normal model where the center is at 12.5, the same values I have here, and the standard deviation is 5/2, or 2.5. Now what do I mean by this statement over here? And what I have, basically, is a couple examples here. All right, let's focus on the one in the upper left-hand corner first. Unfortunately, we can't see a lot here, but okay. Now what I've done here is the following. I'm looking at a binomial distribution where the number of trials is 40 and the probability of success is 1/16. What is the product of NP? It's actually 2.5. The product of n times q is 37.5. These two values will always sum to 40, or will sum to n. In this case, n is 40. Now, what I've done here is between 0 and 40, which is the number of successes I can observe, I've created a little rectangle above the values 0. You can't see the rectangles after about 8 here, or 9, whose height is the probability. And the width here is 1. The scales are different on the horizontal than they are from the vertical. So this rectangle plus this and so forth is simply the probabilities. The areas are the probabilities of observing 0, 1, 2, 3, 4, and so forth number of successes. Now what I've done is I have plotted, in addition to this, a normal model where the center is at 2.5, that's our mean value, and 0.88 is the standard deviation. Now you'll notice that the red curve is a little bit different from the rectangles, but it's not too bad. But I would not use a normal approximation in this case because this is too small. Let's look at another example. Suppose instead of having a probability of 1/16, I have 1/8. Again, these rectangles represent the probability histogram associated with the possible values from 0 to 40. It looks like the corresponding normal model has improved a little bit. It's not too bad, but I still would not use my normal model. Now, if I look here, I have, again, 40 trials. I've moved up the probability of success to 1/4. In that case, these two values, both of them, are greater than or equal to 10. So I would consider the rectangles here as being nicely represented by the red normal model. And if I go further, in this case, where I change the probabilities of success to 1/2, again, there's a very nice fit between the red curve and the tops of these rectangles. Okay. Now, I think I went through an example where I added the areas of the rectangles that I got from Excel, and then I did the computation using a normal model. Okay. So I'm going to put that off. I don't want to do another one right at the moment. Okay? But the point is, the normal model fits the tops of these rectangles or this probability histogram very nicely. So what I can do, suppose I want to know, let's see, this is 20, that's 19, that's 18. Suppose I wanted to know what is the probability of observing 18, 19, or 20 successes in this example here. I could go and use Excel, or what I can do is I can note the following. If this is centered at 18, the left boundary is 17.5, and if this is centered at 20, the right side is at 20.5. So from 17.5 to 20.5, I can instead use the normal model and use those two values, convert them into z-values, and then use my table to find out the probabilities. And those two values should be very close. Now this right here is simply trying to reinforce the notion that instead of using the binomial distribution, okay, which is the exact model that's appropriate in any circumstances, we can instead use a normal model. Okay. And here's another example where I have a binomial distribution with 30 trials and a probability success of 0.35, and I have all the little rectangles which represent the probabilities of success from 0 on up to 30. The width of these rectangles is 1, the height is their probability. And then I superimpose on top of it the corresponding normal model. Now, again, keep in mind when looking at this graph here, first of all, you don't see any rectangles over on the right. Why is that? They're so small you can't see them. They're minuscule. And the same thing is true on the left. Now the scale on the horizontal is different from the scale on the vertical. Between the tick marks here, it represents 1 unit, whereas 1 would go from here, maybe all the way up to there. So I've magnified the vertical direction, because if I didn't, you couldn't see these rectangles. Okay. Chapter 17 also talks about what's called the Poisson distribution and the exponential distribution. It also talks about the geometric distribution. None of those I discuss here in class. Okay? So I need to add into my overheads that we don't discuss the geometric distribution. Okay, now, what I did then is basically said the following. In fact, this is maybe where we should look at this problem over here on problem number 23 on page 475. So let me diagram that. I have a population excuse me, of children in Britain. And there's a certain value. Let me diagram it in the following way. In this large population of children, which is probably several million, they either have rickets or they don't have rickets. Now, in this population, there are two things. You either have rickets or you don't. Now, what we do is we use little p to represent basically the number of children with rickets number of children with rickets divided by the population size. And Q, which is equal to 1 minus P, turns out is actually the number of children without rickets. Divided by the population size. All right, now, we don't know what P or Q is. Further reason you probably don't, there's probably some tests you run. Tests cost money. If you were to spend all that money over several million kids, you're talking about a lot of money. All right? And I suspect that probably the way in which doctors treat rickets would be kid comes in and maybe he's broken some bones, maybe. And they take an x-ray and they see that the bones are not really strong. And then they do some tests to figure out why that's the case. And then they go from there. All right, so what we're doing here is we have a situation where there is a P, we just don't know what it is. Now what we do is we sample from this population. You can think of this as being representing a great big bin or urn of children. I reach in, I randomly select one of the individuals out, all right, and I determine whether or not they have rickets. All right? And then, for the purposes of discussion, I'm going to assume I put them back in the urn and I mix it up again and draw a second one. So there's a chance I could draw that first person again, but it's very, very small. The mathematics is a little easier if we assume that we put them back in and draw out a second, okay? So anyway, we sample. We take a sample size. So we take a sample size. And in this case, the problem says what? 2,700? Okay, so we're going to look at 2,700 kids, and we're going to perform this test to determine whether or not they have rickets. Now, let X be represent the number of children with rickets. Now, X could be as low as 0, very, very unlikely. Could be 1, 2, all the way on up to 2,700. Again, not likely 27, but we could actually compute a probability. Now, what we do is we look at something we call p hat, which is the number of individuals with rickets divided by the total sample size. All right, now, what they say here is the following. In this particular example, 20% were deficient in vitamin D. Now I know what N is, and I can figure out what X is. Actually, in other words, if the total sample size is 2,700, 10% would be 270, all right? And if I claim that 20% had rickets, that means X was equal to twice 270. So X apparently was twice 270, which would be 540. So apparently, of those 2,700 students, or children, 540 had rickets. Now what's the relationship between p hat here and this value p here? Well, we think of p hat as being an estimate. P hat is an estimate of p. Now that's probably a pretty good estimate, provided I do my selection of children randomly. That is without knowledge of anything about them. I just reach into this great big population, I pull 2,700 out, and I determine how many have rickets. Now what we'd like to do is the following. First of all, this 20% suggests as a single number. That's a good estimate of p. So apparently 20%, based on this study, of children in Britain have rickets. Okay, now, we have a little bit more information than what I've stated here. Not only do we have an estimate of p, we can actually come up with two numbers, which is called a confidence interval. And we'll be able to say, with a certain degree of confidence levels are given percentages, maybe 90%, 95%, or 99%. In this particular problem, they use 98%. But I'll come up with two numbers and I'll say I'm a certain percent confident that the real value of P is between these two numbers. All right, now let's take a look at the how we go about thinking about this. This is the way we think. I have a normal model. In other words, I'm automatically saying we'll treat X as being normally distributed. So we'll treat X as being normally distributed. X actually has a binomial distribution, but we have such a large sample size, probably the approximation by a normal model is almost certain to be correct. Okay, now I don't know, again, what P is. Presumably, I can think of X as being, or excuse me, I can think of P hat. P hat, the observed proportion, is approximately normal, where the center is at P, and the standard deviation is the square root of P times Q over N. I know what N is, but I don't know what P and Q are. So what I've done is I've gone out, and this horizontal line represents possible observations, or possible observations of P hat. So I got a value of P hat, and I don't know whether it was bigger than P or less than P, but it probably is pretty close to P. This is what we observed, just like if I flip a coin, and I flip it 25 times, I might get, say, 12 tails, or maybe 11 tails. What would P hat be in that be? It would be 11 divided by 25. That's the observed proportion of successes. Now, what I'm going to do next is the following. I'm going to mark a point over here, which is P plus 1.96 times the square root of P times Q over N. And I'm going to mark a corresponding or symmetric point over here, which will be P minus 1.96 times the square root of P times Q over N. The significance of the 1.96 is the following. This right here is then 95%. The probability or the chance that I will observe a value P hat between these two limits is about 95%. The problem here is I don't know what these values are. If I knew what P and Q are, I wouldn't do this survey. Okay, now, in saying that P hat is between these two values with probability 95%, actually what I'm saying is that P minus P hat, the absolute value of their difference, is less than 1.96 times the square root of P times Q over N with 95% probability. Again, I'm not certain that this is the case. All I'm saying is if I take the absolute value of the difference between P Again, I don't know that. I'm assuming there is some value. But if I take that difference, take its absolute value, it will be less than this amount with probability of 95%. So I'm going to write this. The problem here is as follows. Again, we don't know what this is. Here's the punchline. We estimate the square root of p times q over n by the square root of p hat times, and I can write this as 1 minus p hat, which we also call q hat, divided by n. Even though I don't know what p is, I know what an estimate of it is. I don't know what q is, but this would be an estimate of it. And this quantity is the theoretical value. This is the observed value. I call this the standard error of p hat. And basically we're saying we estimate the standard deviation of p hat by the standard error. Now, what this means is the following. I don't know what that, but what I can say is the following. The probability that p, the absolute value p minus p hat, is less than 1.96 times its estimate, p hat, times 1 minus p hat. Again, we also refer to that as q hat, divided by n. That's going to be approximately 95%. Won't be exact, but it'll be close. Now, basically, this is equivalent to saying, reporting the following. I say the observed value is p hat, I give you that number, and this number right here is what we call our margin of error. So the margin of error which is sometimes abbreviated to say ME, or sometimes just M, is in this case computed by taking 1.96 times the square root of p hat times 1 minus p hat, with that quantity all over n. In this case, p hat is 20%, and as a decimal that's 0.2. 1 minus p hat would be 0.8, and I'm dividing that by 2700. Now if I do the computation here, it says 98. I am doing 95. We'll get to how that would change things here in a moment. So if I take and I compute this, say I want a square root, I guess, 0.2 times 0.8 divided by 2700. All right, and I get the following. I get 0.0076 9 and so forth. So in this case, we would write this as 0.76, 0.769 and so forth percent and we would write the following. The observed value of p hat, what we do is we take that value and add and subtract from it the margin of error. So in this case, p hat is 20% or 0.2. And the margin of error is this. I'll write it as a decimal, 0.0079 and so forth, 69 and so forth. And what I'm going to do now is I'm going to compute 0.2 minus that quantity and 0.2 plus that quantity. This is an expression to say basically there are two numbers. One number is this plus that, and the other number is this minus that. So if I take 0.2 and I subtract that quantity, I'm going to get the following. I put down the first number, 0.19, 2, 3, and so forth, comma, and then I'm going to take 0.2 plus that number, and I get 2.0769 and so forth. Oops, how about 0.2? And well, I'm going to write it down. I'm going to convert this into a percentage. 19.2%, comma, 20 point, I'll round that up to 8%. And we would say the following. We are 95% confident P, the actual value, which I don't know, is between 19.2% and 20.8%. Now, we're not certain that P is between these two values. One way of thinking about the 98% is as follows. 98% of the time when I go through this process, the resulting value P would lie between these two values. 2% of the time it would be outside. I'm sorry, I didn't say that right. 95. 95% of the time when I go through this process, the value P actually lies between these. About 5% of the time it does not. Okay, now. So in getting this value of 20%, which is the observed value P hat, we have more information. We can construct what we call a margin of error. A margin of error is basically, I take a value, this is what I call in my overheads a Z value. You'll see that.
If we multiply this percentage to swallow by 1.96,
well, okay, yeah, I'm taking this value, 1.96 times this.
Yeah, 0.2 times 4.
Oh, thank you. I made a big mistake here. Woo! I thought that looked awfully small. I dropped my 1.96. All right, so that's big boo-boo. At least one person's awake in class, I'm not. Let's do that. And that's going to change our results. All right, so let's see. I need to take 1.96 and I multiply that times that. I get the following. This is going to be 0.015, 0 and so forth, which also can be written as 1.5 and so forth percent. So what I need to do is I need to change this here to be 0.015 and so forth. I need to recompute these. All right, so 0.2 minus, this will be 8.1849, okay, 1 and so forth. And the other value I get 0.2150, okay, and so forth. This becomes 18.5%. This becomes 21.5%. And then these will change. Those numbers that I had up originally look kind of small, so at least I hope that's a little better. All right. Again, the significance of these two numbers is basically that, again, because I've chosen a 95% confidence level, this right here, we call this Z star. This is based on confidence levels, what we call confidence level. So, and in this case, the confidence level is 95%. So from the 95% confidence level, I get 1.96 as my, what I call my special value Z. I do the computations and I end up with what we call a margin of error of 1.5%. And when I take that and add and subtract from that, my observed value p hat, I end up with these 2%. And I say I'm 95% confident that the true value of p is between those two limits there. All right, now, this is how we make use of the idea of a binomial experiment. We're randomly selecting, in this case, 2,700 observations from that population. Okay? We're looking at p hat, which is the actual observed proportion of individuals with rickets. All right? We make use of the fact that a binomial distribution can be approximated by a normal distribution. The model says that my value of p hat is going to be between these two values here, determined by this, with 95% probability. I don't know what these are, so what I do is the next best thing, I estimate them. I take p and replace it by p hat, and q replaced by q hat, which is nothing more than 1 minus p hat. I come up with what we call the standard error of p hat, and then I claim the distance between these two numbers. Basically, the absolute value of the difference of two things is the distance between them will be less than this with 95% probability. See, I don't know whether p hat is bigger than p or less than p, but I know that it's within 1.96 times this value with 95% probability, and within 1.96 times this value with approximate 95% probability. This value here it will in general be very close to that value there. Okay. Now, what I want to do, let's go back to the overheads here. In 18, we introduced the notion of p hat. P hat is simply the number of successes divided by the number of trials. It's a random variable. Its mean is this. The mean, or the expected value of p hat, is p. That's the center value. The variance of p hat is this. The standard deviation of p hat is this. That's where I got for my normal model, my p and the square root of p times q over n. So what I did is, instead of looking at x as a random variable, I looked at p hat, and the normal model I use has a center at p and a standard deviation of the square root of p times q over n. Behind the board, these were the two numbers I was using in my model. Okay, now, this is the formula, basically, that I use to construct my confidence interval. I take my center, or my observed value p hat, and I add and subtract from that to get two numbers, a value of z times the standard error of p hat. Question is, well, what is z star, or z splat? It's a z value. The z value is depends on the confidence level we select. How certain do we want to be that the true value of p will lie between my two numbers? Well, if I want to have 95% confidence, then I use that value. If I want to be 95% confident, I use that value. And if I want to be 98% confident, I use that value. Where do these values come from? Well, if I look at the standard normal model, center is above 0, between 1.645 and its negation, this right here is 90%. If we look at the same standard normal model, centered at 0, standard deviation of 1, between 1.96 and negative 1.96, this area right here is 95%. And I won't do the last drawing, but between negative 2.576 and positive 2.576, between that range of values under a standard normal, all right, we have 99% of our area. When I translate those into an arbitrary normal model, I take those numbers and I multiply times the standard deviation. So that's why see, this comes from the normal model, and this is our estimate of the standard deviation. Now, when you hear the results of a political poll, what do? They tell you a certain percent, and then they tell you a margin of error. Now, typical margins of error, I think, are about 3%. What they don't tell you is the confidence level that they used. All right? In general, most polls, I believe, use a 95% confidence level. So what you do is the following. You can take your center value, the value that they report, subtract from it the margin of error, add to it the margin of error. You're going to come up with two numbers. The poll is saying we're 95% confident that the true value of P lies between those two values. You're never certain when you take a poll. There's always, if you will, a range of plausible values. Now the question is, or one question might be, well, why would you use a 90% or a 95 or 99%? That's an excellent question, without an easy answer. Those are typical choices, all right, but you don't have to make those choices. Generally, your confidence level has to be somewhere less than 100%, but more than 0%. You could use a 99.9% and you could go to a table of a normal table and figure out the corresponding value of Z. You could use a 50% confidence level, but that's usually considered not sufficiently wide. We want to have a bigger interval, if you will, as a rule, than just to be 50% confident. Okay, now, in general, when I ask questions, these are confidence levels that are used. However, occasionally the author does switch to using another value, and let me illustrate how you can figure that out. I don't have this on the web yet, but let's. All right, in the back of your book, there is what's called a t-table, and it follows the standard normal table. So if you look in the back of your text, the first table is the table of random numbers, and the next table is the standard normal distribution, and the next table after that, you will see in the upper right-hand corner, upper left-hand corner, table T. Most of this table we don't use in this class. If you come back for 244, we'll use it a lot. But there is one part down at the bottom that you can use. Let's see. In the table I gave you, in the overheads, I had 90%, 95%, and 99%. And the Z values were 1.645, 1.96, and 2.57. We could have a confidence level of 80%, in which case the value would be 1.282. Or if you use a 98% confidence level, which is what the question, this specific question posed, you would use a value of 2.326. So it's at the bottom of table T. You're too far in your, so it's right after the standard normal table. It's one page. I have on mine, okay, page A66. All right, and what I've done here is the following. Oh, you got cheated. You got cheated. Well, if you don't, I'll put this up on the class web page. What I've done is I've kind of grayed out the center part because we don't use that. It's only the very last line, 2 lines. Yes?
Just to clarify for me, when you put Z asterisk, that was this table T.
Yeah, this is.
So we wouldn't look at the other table T. right? Just the-
Yeah, this is the Z asterisk, yeah,
Okay.
that line here. Now, whew, sometimes the notation must seem like it's a torture, you know. The Z stars, I think of them as being special values of Z, okay? These values of Z are actually derived from the standard normal table, but they're kind of pulled out and given to you directly here, so you don't have to figure them out using the table. Although you could get these values here. You could determine that. In fact, we had a problem probably way back when, where we did something equivalent. But I'm not sure I should ever test fate by asking you to actually show these, at least in 243. But usually in 244, I do have people figure out some values of these stuff. Okay. So your table in the back, this is not going to be grayed out. I do that because we don't want to use any part here. This row here, think of that as being associated with the standard normal. And these are Z values, my values of Z star. Okay, now. Oh, well, I think it's time for a break. What I'm going to do here is we're going to, well, first of all, this is what I look at. P hat, we think of it as being a sampling distribution. It's a, if you will, what can happen when we sample from a binomial or from a population where I have things called success and things called failure. Okay, these are some of the, you know, again, these results here actually come from the random variable x, which has a binomial distribution. And if you look at the values, the mean value and the variance for x, and use the rules that I have stated and expected you to know for computing means and standard deviations and variances of new random variables, these values here come from those rules. Okay? Surprising as that may seem. Okay? So anyway, these values here, we basically just make use of them, and we make use of them in the way that I've described. Okay, P hat is sometimes called the sample proportion of successes. Polling results are reported as proportions of successes. We use the normal approximation when NP and NQ is greater than 10. Generally, we don't know what P and Q are, but we assume that they are. And that's because we're doing really large samples, 1,000, or maybe 2,000, or 2,700 in this example. So typically, in polling, we're assuming that these criteria are valid. The sample proportion, if someone else did exactly the same test, they go out and randomly select 2,700 children in Britain, determine whether they have rickets, they'll probably get a different value of P hat. P hat is a random variable, but the values of P hat, even though we will vary, they should in general be close to the true value of P. And we construct a confidence interval as a way of describing where we think a range of plausible values for the true value of P is. All right. Let's take a break for about, I guess maybe 12 minutes or so, and we'll resume, and we'll actually look at another example of this when we return. Well, we'll take a break for about 12 minutes. Stapler? Okay. Use that knife. I'm sorry, how many? Well, I think the total number of points is actually 108.